In this video, we're going to go over heating curves. So heating curves show the input of energy to either heat a material up or cause it to change state. And then I'm going to show you a PhET simulation that shows what's actually happening at each of those points so that you can actually understand why the slope is different at each point or it requires more of an input of energy for something to happen. So at first, you heat up a solid. Then you reach a temperature which, under those conditions of pressure, something will go from the solid phase to the liquid phase. And that process is called melting. If you're going in the other direction, it would be called freezing. So melting requires an energy input. And you might have noticed this, that when you heat up ice, if you put a thermometer in it, it's going to stay 0 degrees the whole time until all the ice is melted. And then it can start heating up again. So you're inputting energy without a temperature change at that point at which you are melting. Once it all melts, then you input energy again and you can heat up that liquid. So the liquid's temperature increases until you get to the point where that liquid water is now boiling. And if you actually put a thermometer in boiling water, you would notice again that it stays the same temperature the whole time. Your thermometer would read, if it's pure H2O, 100 degrees Celsius for the duration of its boiling. And then if you could collect this steam and continue to add heat to it, then and you recorded the temperature change as it was going, you would see that you could then heat it. Now, you might notice that each of these lines has a different slope. And you also might notice that melting a material requires less energy than boiling it. So, heating a solid, only requires 2.18 joules per gram for water. Heating it as a liquid requires 4.184 joules to heat a gram. And then again, it requires a lower number as a gas. So it requires more energy to heat up a gram of water by 1 degree Celsius than a solid. And you also should notice from this that it takes more energy to boil a liquid than it does to melt a solid. So we're going to use what we just learned about heating curves and what's happening as you have materials going through different transitions to calculate the energy required for 5 grams of ice to go from negative 20 Celsius to 110 Celsius. So obviously at negative 20 you have solid ice until you get to 0 degrees, at which point you're going to have to melt the ice, and then it's going to heat up as a liquid from 0 degrees to 100 degrees, and then it's going to boil, and then it's going to heat up as steam. So how we quantify these values, Q again represents the heat transfer, and then C represents the specific heat of a material, M represents the mass, and delta T represents the change in temperature. So when you're approaching a problem with this, you have to really look at each component individually, and then you're going to add it all up at the end. Also, I just want to point out, you can go a couple different ways with this. You can go from just determining the total value, or you could be given the total value and then most of the components, and then you have to figure out the missing piece. So that's how we could approach these problems. So first, going from negative 20 to 0 Celsius, you multiply by the specific heat of ice, which is less than that of liquid water. It's only 2.11 joules per gram degree Celsius, where water is 4.18. That has to do with what's going on when you're heating it. So as solid ice, they're in fixed positions, so overcoming those, making the vibrations happen, you're not actually competing against as much. When you guys are liquid, you have basically the intermolecular forces being applied continually with a greater density of material. You actually have more energy being required to increase the temperature. Then again, as a gas, the specific heat drops down again. You have molecules that are farther apart, so when you're adding the kinetic energy, it's just going straight into the motion of the molecules and not actually overcoming any other forces before they're able to move. So here we go. Specific heat times the mass times the change in temperature. So we got 211 joules to go from for 5 grams of ice to go from negative 20 to 0. Then to actually melt the ice, you multiply. The heat of fusion is usually represented as a molar value, which I just converted it to grams, joules per gram here, to make all the equations simpler here. So you have 333 joules required to melt a gram of ice. Since you have 5 grams, that requires 1,670 joules of energy. For the water, you have a specific at 4.184, 5 grams, and 100 degrees change, because it'll go from be a liquid from 0 to 100 degrees Celsius. That's your amount of energy that needs to be input there. And then you have to boil it at that point. Notice it takes substantially more energy to boil, again, than it does to melt, because you are completely overcoming the intermolecular forces, not just letting them get shifted around. So 2,260 joules per gram times 5, that's the energy input to boil it. And then to heat it up again as gas, you multiply the specific heat times the mass times the change in temperature. This all required a total energy input of 15,400 joules, when rounding to 3 sig figs, because that's what we would have to do with the information given in the problem.